A massive slab of concrete, weighing 10,000 kilograms, tears away from the spillway floor, tumbling into the abyss like a discarded toy. The roar is not just water, it is the sound of 80,000 tons of kinetic energy, grinding bedrock into powder. Steel rebar snaps with the crack of a sniper's rifle, as the mountain itself begins to dissolve. The very structure meant to protect California from a watery grave, is now eating itself alive. One catastrophic chunk at a time. This isn't just a leak, it is a structural heart attack. This moment of collapse is the culmination of trillions of tiny molecular betrayals. Where the bond between cement and stone finally surrenders to the relentless hammering of fluid dynamics. To understand how the tallest dam in the United States nearly became the source of a biblical catastrophe, we have to look past the surface and into the terrifying physics of water under pressure. Let's find out. Most turn away. But here at Surphysia, we decode the math behind the chaos. Support the mission by subscribing now. The Oroville Dam stands as a monument to human confidence. A colossal wall of earth and rock, rising 235 meters into the sky. To visualize that height, imagine stacking over 60 school buses end-to-end vertically. It is a massive barrier holding back over 4 cubic kilometers of water. That is 4 trillion liters of potential energy. A weight so immense, it literally depresses the Earth's crust beneath it. For decades, it sat as a silent guardian. A triumph of 20th century engineering designed to tame the Feather River. But in February 2017, that confidence met the reality of a changing atmosphere. After years of brutal drought, the sky opened up. An atmospheric river, a literal conveyor belt of moisture stretching across the Pacific, began dumping trillions of liters of water onto the Sierra Nevada foothills. The reservoir didn't just fill, it surged with the violence of a bathtub being filled by a fire hose. When engineers opened the gates of the main concrete spillway to manage the inflow, they expected a routine release. What they got was the beginning of a nightmare. Halfway down the 900-meter concrete slide, a tiny, invisible fracture existed. It was a flaw hidden beneath the surface. A product of decades of slow erosion, and the relentless pressure of water that had seeped into the drainage systems. As the flow reached speeds of over 30 meters per second, faster than a car speeding down a highway, a phenomenon known as stagnation pressure took hold. Water was forced into the crack at such high velocity that it acted like a hydraulic wedge. Imagine a crowbar made of liquid, shoved under a concrete slab with the force of a locomotive. The pressure built, until the concrete simply couldn't hold. A section of the floor erupted upward, and the water began to dive beneath the remaining slabs. The physics here are brutal. When water moves at 30 meters per second, its kinetic energy is proportional to the square of its velocity. If you double the speed, you quadruple the destructive power. Within minutes, the smooth concrete highway for the water was gone. In its place was a jagged, expanding crater. The water, now untethered, began to strike the soft soil and weathered rock beneath the spillway. This is where the physics of erosion becomes terrifying. Water at this volume and speed carries more energy than a fleet of bulldozers. It doesn't just wash away dirt, it hammers it. Cavitating the very air bubbles within the flow to create micro-explosions that shatter rock. The soil was excavated at a rate of hundreds of cubic meters per minute. The canyon wall began to disappear, dissolving like sugar in a hot cup of coffee. Engineers were forced into a choice that no one ever wants to make. Keep using the broken spillway and risk the entire mountain washing away. Or stop the flow and let the reservoir rise until it hit the emergency spillway. A feature that had never been used in the dam's 50-year history. They chose the latter. They shut the gates. But the water kept coming, fed by a watershed that was bleeding melted snow and torrential rain. The reservoir level climbed centimeter by agonizing centimeter. Each centimeter represented millions of additional kilograms of pressure against the dam's face. When the water finally topped the concrete lip of the emergency spillway, it didn't flow onto a prepared surface. It flowed over a raw, dirt hillside. Human hubris had assumed this would be a once-in-a-thousand-years event. And thus, the emergency spillway was never armored with concrete. It was just a grassy slope. A vulnerable flank on a multi-billion-dollar fortress. As the water cascaded over the edge, it began to do what water does best. Find the path of least resistance and exploit every weakness. The erosion was instantaneous. Small trickles became deep gullies. Gullies became ravines. The water was moving at a volume equivalent to several Olympic-sized swimming pools, passing a single point every second. This wasn't a gentle overflow, it was a liquid chainsaw. The fear wasn't just that the water would escape, the fear was headcutting. This is a geological process where erosion moves backward, toward the source. As the soil at the base of the spillway washed away, the waterfall moved closer and closer to the concrete weir. The only thing holding back the top 10 meters of the reservoir. It was a race against time, where the prize was the survival of the valley below. If that concrete were undermined and collapsed, a wall of water 10 meters high would have surged down the valley. We are talking about nearly 500 million cubic meters of water, released in a single, violent pulse. The pressure at the base of such a wave would be immense. Over 10 bars of pressure, comparable to the weight of a school bus pressing down on every square meter of your body. Such a wave doesn't just flood, it obliterates. It would have leveled towns like Oroville and Marysville. Turning homes into kindling and cars into shrapnel. Moving with the unstoppable momentum of a mountain in motion. The sound during those hours was a low-frequency vibration. A sub-bass drum that could be felt in the chest of anyone standing within a kilometer. It was the sound of the earth being stripped naked. The groan of a landscape being remodeled in real time. The air smelled of wet stone and pulverized pine trees. A sharp, metallic scent of broken earth. As the emergency spillway continued to fail, an evacuation order was issued for nearly 200,000 people. Imagine the irony. A structure built for safety was now the primary threat to survival. People fled with nothing but what they could carry. Leaving behind a valley that was minutes away from becoming an inland sea. Their lives suspended on the strength of a crumbling hillside. Back at the dam, the engineers realized the emergency spillway was failing much faster than the broken main spillway. They had to pivot. They reopened the gates to the main spillway, even though it was already a ruin. They sent 100,000 liters of water per second, down a shattered concrete path. The result was a spectacular display of destruction. The water hit the crater in the main spillway and launched into the air, creating a rooster tail of white water 60 meters high. The spray was so dense it created its own microclimate. A freezing mist that coated the surrounding canyon. But it worked. The massive flow down the main spillway lowered the reservoir level, just enough to stop the water from pouring over the emergency weir. They were essentially sacrificing the spillway to save the dam. The immediate crisis was averted, but the cost was staggering. The main spillway was a jagged scar. A canyon within a canyon. The hillside was a moonscape of boulders and mud. Stripped of all vegetation and topsoil. Over the following months, the repair effort was a feat of industrial strength that rivaled the original construction. Thousands of workers moved millions of kilograms of debris. They used specialized high-strength concrete designed to withstand the shear forces of water moving at highway speeds. Concrete that generates so much heat as it cures, it has to be cooled with internal pipes. They anchored the new slabs deep into the bedrock, with steel bolts 5 meters long. They weren't just rebuilding, they were over-engineering to compensate for the lessons learned in the mud of February. The physics of the Oroville crisis teaches us about the deceptive power of the small. It wasn't a massive earthquake or a terrorist attack that nearly destroyed the dam. It was a tiny crack, and the relentless, compounding force of water molecules. When water is confined and pressurized, it behaves less like a liquid and more like a solid abrasive. It can cut through steel. It can shatter granite. At high enough velocities, water creates vacuum bubbles that implode with enough force to pit the surface of stainless steel, a process called cavitation. And when we build structures to contain it, we are entering into a permanent contract with the laws of thermodynamics. We provide the container, and nature provides the entropy. We often think of our infrastructure as permanent. As static objects that exist outside of time. But every dam, every bridge, and every skyscraper is in a constant state of decay. The Oroville incident was a reminder that maintenance isn't just a chore, it is the thin line between civilization and catastrophe. We spent hundreds of millions of dollars to fix a problem that started with a few centimeters of neglected concrete. The irony is thick. We have the technology to move mountains, yet we are often defeated by a bit of moisture and a little bit of time. The structural integrity of our world is often held together by the thinness of a coat of paint, or the tightness of a single bolt. As the new Spillway stands today, it is a testament to what we can do when we are forced to face our failures. It is stronger, deeper, and more heavily armored than the original. But the water is still there, waiting. It sits behind the wall. A silent weight of billions of kilograms. Pressing. Searching for the next microscopic flaw. The atmosphere continues to shift, promising more intense atmospheric rivers and more rapid snowmelts. The math of the next 100 years suggests that our once-in-a-lifetime disasters might become a decade-long recurring theme. Challenging the limits of our materials and our foresight. We decode these moments not to spread fear, but to understand the scale of the world we've built. We live in an era of giants. Surrounded by engineering marvels that we often take for granted, until they begin to groan under the weight of the universe. The Oroville Dam didn't fail entirely. But it gave us a glimpse into a world where our control is an illusion. It showed us that gravity always wins. That water always finds a way. And that the materials we trust, concrete, steel, earth, are only as strong as the physics that bind them together. Every structure is a temporary pause, in the inevitable flow of energy from high to low. The universe is full of chaos, but we are here to decode it. Stay connected to Surphysia.